Okay, so I've reviewed binomial square structure with you, and this is, and the way you find these in textbooks in general form is a minus b quantity squared. You square the first, double the inner product, the product of the terms, minus 2ab plus b squared. And down here, a plus b squared is equal to the square of the first plus twice the product of the terms plus the square of the last. Not too bad. And while we're at it, there's another real common one that you've had from beginning algebra. If you have a, what if you did not have a middle term over here? Zeroed out. And you only had the square of the first and the square of the last, and it happens to be the difference of the squares. Not the sum, but the difference. This factors a minus b times a plus b. So if you ever see what's called a difference of squares, if you ever see a difference of squares showing up, and it might look kind of strange, but if you see a perfect square minus another perfect square, you know it can factor into something like that. You want to do an example? Just so you'll be ready for when you see it a little later? Okay, how about 64x to the 6th minus 81. Isn't this a perfect square? Right? 8 times what squared? X cubed, right? Minus 9 squared. So it's a difference of squares. So it's an 8x cubed minus 9 times 8x cubed plus 9. All right. That's the fundamentals that I wanted to go through with you. We'll review numerous other fundamentals as we go through this course, because if you're anything like the way I was when I was a student, don't remember things real well, you know, from one term or over a course of a summer or something like that. So if we keep coming back to these fundamentals with you, then eventually it'll stay in your head a little longer. Okay. Any questions? Any other questions regarding homework? Okay. Only 1 or 2 of you have come to see me individually, so please do so. I'm available in the Math Resource Center, so come see me. I'm glad to help you, particularly those who had some trouble on that quiz. And a couple of you I noticed didn't even take it. So I will be either emailing you or talking to you maybe tomorrow in class. And tomorrow, while I'm at it, let me remind you where we're going to be. It's on your syllabus. I believe we're going to be up in the computer lab again tomorrow. Okay, room 222 over in the math area. Okay, and we'll do some group activities and then do some other things with Math Excel and the calculator tomorrow from 10 to 12. Okay, ready to do something else? Okay, we've kind of beat circles to death. Okay, so let's talk about graphs and features of functions. Make up a problem similar to what you'd see in the book. So let's say I have a function, call it y, and y is an output value. And if I use the notation f of x, then x is my input value. And let's say I have a quadratic function. How about 2x squared minus 6x? Okay, let's just stick with something like that. So, if we built a table of values with this thing, we could pick different numbers, and this is the way you do it, and you did it back in intermediate algebra, and you may have forgotten, and it's tedious to build a table of values. I'll show you how to use our calculator here in just a moment to see a table of values for a particular function. Is there any input problem here? Any number you drop into this that would cause trouble?
0.
If you put 0 in for x, what do you get for the y?
0.
Okay, 0. And so f at 0 is still 0. Is that trouble? How would that plot on a graph? Goes through the origin, doesn't it? It's just going to go through the origin is all. So is that trouble?
No.
No. It's just like if I have no money in my wallet. Okay, I'm not in trouble. I just don't have any money in my wallet, right?
You've got bills to pay.
Yeah, unless I have bills to pay. Okay, and let's keep it simple. Let's say if I put in a 3, f of 3 would be, do the math, 9 times 2 is 18, minus 18.
0.
Oh, boy. That's strange. Where's that on this picture? This information.
3 on the x.
3, it's an x-intercept, isn't it? Right here. Notice the way I label points. I'm trying to model good behavior, okay? I label points. If I'm drawing it and I'm laying down a point, I label it. Okay, let's do something else. Let's go halfway between 0 and 3. That would be half of 3, wouldn't it? Midpoint, right? Remember how to do midpoint?
Average.
Add these together and divide by 2. 3 divided by 2? You know that's 1.5, but I'd like you to be thinking of the improper fraction, 3/2. So if you put 3/2 into your function here, we have a little bit of arithmetic to do. Twice times 9/4 when you square it, minus 6 times 3/2, and that'll reduce. So we can reduce this a little bit to 9/2. Now, I could reduce the 2 into the 6, couldn't I? But notice that I have 9/2 right here. Why don't I leave this with a fraction of a half? Halves in there. Minus 18/2, so that I can have a common denominator and see the result. So 9/2 minus 18/2 is negative 9/2. Where does that plot?
Four.
3/2 is halfway between here and down 1, 2, 3, 4, 5, 4.5. Right down here. 3/2 minus 9/2. What shape do we get if we plotted an infinite number more of points?
A parabola.
We're going to get a parabola, which you have seen before. And it's going to have symmetry to this spot between these x-intercepts, or these zeros. And the graph will look something like that. This point down here looks like it's going to be the bottom point, happens to be called the vertex. Vertex. Typically you label that with a capital V, and that's called the vertex. Now all of you have seen this before, this stuff before, but I need to review it with you because how many of you did not remember it very well? Most of you. Okay, that's not uncommon. Okay, and we'll be getting to this particular function in more detail real soon. I just wanted to use this to illustrate some of the features of a graph. So what are some of the features that you see coming off of this graph? You see that it has zeros. Happen to be at the origin and at 3, 0. Okay? It has a y-intercept. And where is that? Happens to match this particular 0 because the y-intercept is where it hits the y-axis, and so that's the point 0, 0 also. This point down here is called the vertex, and on this type of parabola that opens upward like a smiling face, this is the bottom of it, and we call that the minimum. Minimum, the value happens to be minus 9/2, and it occurs when the input is 3/2. So it occurs at 3/2 minus 9/2. A couple other features is that this particular function, this is called a second degree polynomial. A second degree polynomial. That should be familiar vocabulary. It might be new to some of you. The reason it's called second degree is because in any given term, you look at the degree of the variables and add them together. In this case, there's only the variable x, but notice this has exponent of 2. That's why it's called second degree. This other term over here is a first degree or linear term. So this is a second degree polynomial. Polynomial means many made up of several terms. In this case, only 2 terms. All right. This particular polynomial ends up trending to the left, up left, doesn't it? And you're going to hear me say that kind of thing a lot later in the course. Up left and up right. Not a single word, but up to the right. What is the function doing as you move from left to right in the left half of the domain?
Decreasing.
It's decreasing. It's falling as you come down to this point. So it's decreasing in this region where you see it falling as you move across from left to right. In other words, the inputs are increasing, aren't they? As you move across here, the inputs are increasing as I move to the right. And as I keep increasing my inputs, my outputs are decreasing until I get to this location. And then beyond this location, as the inputs continue to increase, the outputs now are starting to increase. So we have decreasing in this region, and we have increasing over here to the right. There's an interval that it is decreasing in. What's the domain of the function? Let's go back up here. What's the domain of f of x?
Negative infinity to infinity.
Negative infinity to infinity. Now, can you ever get to infinity?
No.
No. If you told me a number that you said was infinity, couldn't I tell you something bigger or smaller than that?
So,
Yeah.
you don't include
So it's
infinity.
unbounded. So what we use in our interval notation is parentheses to indicate that you can't ever get exactly on that value. What's the range of this particular function? Negative 9/2, that includes it, doesn't it? And how high can it go? Think of the water level. Starts down here, goes up to infinity, doesn't it? But you can't get to infinity. This is called a half open or half closed interval. Half open or half closed interval. This is the kind of notation we're going to be using from this course onward. Okay? So that's quite a few features. We've got zeros, a y-intercept, minimum in this case. We have a domain and a range. Oh, what's the interval where this function is decreasing?
Negative infinity to 3/2.
The decreasing interval off to the left, always smaller to larger, off to the left, the inputs can be negative infinity, that far to the left. How far to the right?
To 3/2.
To 3/2. Does it include the 3/2 where it's decreasing? No. Is it decreasing when it's at 3/2?
No.
Now it evens out.
Is it increasing?
No.
Is it decreasing? No, it's not doing either, is it? It's bottomed out. So microscopically to the left of that, it happens to be decreasing. Okay, so that's the interval where it's decreasing. The increasing interval would be greater than 3/2. Greater than 3/2. Okay. Pretty basic, but very important vocabulary.